Okay, welcome everyone from our webinar on OpenMP. So this is the 5th webinar on OpenMP in our series. And we have Christian Terboven and Michael Klemm who are the speaker today. So please, Christian, go ahead.
Yes, thank you. Welcome back and good morning to you as well. So what's on the agenda for today? Well, this is the 5th webinar and we continue with the topic of, you could call it GPU programming, or we would call it offloading, because in OpenMP, all the concepts are in principle independent from the target architecture. So while GPUs are the topics of this talk, the same mechanism would also work for a significant range of other accelerators, coprocessors, or whatever you might want to call it. I will start with a very brief review of the homework assignments from the previous webinar, and then I'll talk about unstructured data movement, followed by Michael, who will add more details on the topic of reducing data transfers, because in particular for GPUs, this is important to improve efficiency. Then we will talk about asynchronous offloading, and again, Michael will take over to add more details from real-world application case studies. So the idea here is to put some practice or practical experiences behind the theory. And with theory, I refer to the parts where we were just presenting the elements of the OpenMP language and API. In addition, Michael will also add some details on how to integrate GPU kernels that are or have been written in other programming models, for example, the programming models specific for individual vendors. And then there's just one slide on which I would like to give you ideas on how to work again with the code, the Jacobi code that we provided as the homework. Yeah? So the idea is that you can again add things that you have learned today to the code in order to improve performance. Now I have to switch again slide decks. A second, please. Okay, so last week we gave you two codes. The one is stream, which you could use to measure the bandwidth that you can achieve on, for example, the host and the GPU and compare that. And I think the code that was a bit more interesting was the Jacobi kernel, and we asked you to port it to the GPU. So my plan is to do this live now and also discuss the code changes that I made in order to get the performance, but I wanted to give you an idea about the environment which I will be using in the next few minutes, and also the performance measurements or the performance that I would expect are added as screenshots onto the slides. Yeah, because I'm using an interactive system, and it could happen that when I switch to my terminal window, the GPU is already in use. Then I would have to go back to my slides, but it worked a couple of minutes ago. So I'm using the Tesla V100. This is a Volta architecture. It's a system with SXM. So that means the two GPUs, or the two GPUs in the system are connected via the NVLink interconnect. The host system I'm running is CentOS 7.9, which is Red Hat Enterprise compatible, and I'm using Clang 12, which then makes use of the standard library that comes from the GCC 4.8 series, which is a default compiler on the CentOS or Red Hat Enterprise 7 series. So, oops. Now let me try to share my terminal. And Michael, I would appreciate if you could give me some feedback if this is readable. I think I have to enlarge the font size a little bit.
Works for me. Looks good.
Okay, so I'm on one of the interactive GPU systems on the HPC system in Aachen. And oops, yeah, you can see that there are many different versions of the code. Yeah, and tasks 1, 2, and 3 is what I asked you to do. This is the code that we provided, and we provided both the Jacobi code in itself, but also a possible solution. And let me just show you the difference between the Jacobi code and the solution. The only thing that I added is a pragma OMP target, which initiates the offload. Teams distribute parallel 4. Remember, this performs this blocking of the loop into the different dimensions of the GPU. We talked about that last time. I need a reduction. I added this already, so it's a little bit of a tunable here already. Sorry, and there's a map that makes sure that the data is being put onto the GPU. Let me just show you how to compile the code. Oh, sorry, module load Clang 12, module load CUDA. That's a fresh terminal. So I'm using the Clang compiler. I'm asking for OpenMP support. I'm asking for OpenMP target support, and I'm specifying the target architecture. That's NVIDIA PTX is their, let's say, native or binary code, 64-bit. And again, I have to make use of this flag this is a flag to enable the target support. This is a microarchitecture that I'm targeting on the device, and that's about it. So if I now execute this code, it's a Jacobi solution on the GPU, and you will see that it's really, really slow. So it's a mesh of 16,000 something times 16,000 something. And I'm executing it with one thread. Don't be too confused. We will improve that a little bit later on. I stop after 100 iterations, and you see it takes quite a while for these iterations to complete. And also don't let yourself be confused by this here. So this is if we just offload the computation from the host to the GPU, that means 0 rows are being executed on the host. Using both the host and the GPU will be a task of the next homework. Okay, it's running a little bit, damn it. Still running.
Just kill it and call it too slow.
Oh, it's almost. Okay, yeah, it's a little bit boring. Okay, so let's just take a look at the code here. Oops. Sorry, what did we do? Let me just go to the parallel. Here, this is a single loop that we parallelized, which performs the update of the matrix A by making use of the old matrix. If we take a closer look, this loop is executed within a while loop. That means in each iteration. So in each iteration, we have to transfer data from the host to the device and transfer it back. But in particular, we're not making good use of the parallelism on the device. So your task, and let me go back to my slide, was then to improve the data management. To some extent, we have to admit that this is a topic of this week's lecture. So that means, don't be disappointed if you were unable to fully complete this task. So let me show you the code here. What did I do? I introduced a data environment. This is something that we'll cover in the lecture now. So that means for the whole extent of the while loop, the data of A and will remain on the GPU, and also a new will not be copied from the host to the device, but instead it will be allocated on the GPU. And I executed not only a single loop, but both loops in parallel on the device. That's a significant difference here. Let me compile it. I compiled it already. And if we execute this on the GPU, we will see that it runs significantly faster. I never completed the measurement from the previous task, but I think we're faster by a factor of 10. And let me think about what was the third task here. I looked at scheduling for the GPU. What did I do? So the thing that I intended you to do is to make use of the collapse clause so that both loops are being combined. That means the compiler has a better chance of, has more chances or opportunities. I think that's a better term here. Has more opportunities to optimize the code for the memory and also compute architecture of the GPU. And actually, I also wanted to add this only in this task and not to the solution of the previous of the first task already. And with these two tunables, again, I can execute the code, and I think the previous execution was 7.9 seconds. And again, we just did we just added one clause, and the performance improves again a little bit. So we're now down to 5.7 seconds. However, there's more to what you can do with the code, but the intent is to cover some of these aspects in today's lecture. That was my brief summary. Any questions on these exercises at the moment? Or anything that you would like to add, Mike?
Nope, nothing to add from my side.
Okay, then let me close my slide deck here. So just to understand if I should make remark to the exercises from today's participants, I can't open the window here. How many of you have worked on the exercise? Can you just show us with a hand or something like that?
Christian, there's also a question in the chat. What's the expected performance for a single dual socket Xeon EPIC for these parameters?
A Xeon EPIC?
Yeah, Xeon/EPIC.
I don't remember. Sorry. I could run that later on while you were talking, Michael, if I find an empty machine.
All right, cool.
I don't have the numbers in my head.
Okay, there's another one. Would have improved the performance using the shared memory of the GPU. So would it help to use the shared memory cache of the GPU?
Between the host and the GPU?
No, the on chip or the on GPU shared, underscore shared underscore underscore.
In the context of OpenMP, I would hope that the compiler can generate code making use of that memory. Yeah, but so the challenge, in GPU programming, similar to the challenge for host programming, is always to generate efficient code. And I think with OpenMP, the idea is to give the compiler, in addition with a runtime, the enough information so that the code can run in an almost optimal fashion on the device. Yeah? But so you have seen a few clauses like the schedule clause, the collapse clause, the target data clause. So with that, we are providing more information and also guiding, let's say, the translation of the code to get better and better performance. Yeah? So there's no magic in the compilers. They can't do all for yourself, or all out of the box. Of course, if you find out that special aspects of the compute parts or of the memory are not being used, then making use of, for example, other features in your compiler or features only available for a particular target device can improve the performance of the code. I'm right now hesitant because I forgot if the final OpenMP variant that we might present in the next webinar, or we can also upload it to the GitHub repository. So if that variant delivers the same performance as our CUDA native variant, so I would have to double check on that. But yeah, in my sources or in my repository here, I don't have the CUDA variant. So I can't really tell you if the final OpenMP end version delivers the optimal performance. I don't have that answer available at the moment. I hope that it answers the questions.
Yeah, there's one comment I would like to make. The problem with using the shared memory, of course, is that you need to block for it, right? And this, in stencil codes, if it's too large, you may have to block across the time steps as well to make efficient use of it. There's another question in the chat, and Christian, probably you should look at the chat because there's a piece of code in there. The question is, how do the thread teams, blocks, etc. map to the hardware when you split the OpenMP pragma between the two loops? So having something like teams distribute on the outer level for the J loop, and then having pragma on parallel 4 for the I loop. That's a tough one.
That's a tough question. So I think that's not a good idea. Because it basically depends on the dimensions of N and M. Yeah. So think of the teams. With that, you want to, let's say, exploit the streaming multiprocessor. I forgot NVIDIA's terminology again. So the Mike, can you help me? Okay, remember the picture of the GPU architecture from the previous webinar. Sorry for that. We talked about the CUDA core and then the cores sharing the caches, and they are organized in so-called blocks. Yeah? We want to make use of these different, of this hierarchy in both the memory and also for example, the capabilities of the device to synchronize threads and so forth. And we want to exploit this hierarchy also in our parallelization. That's the idea. And this is why we have to use teams distribute and the parallel 4. So if N and M are really large, I think teams distribute, the N is too large for the teams distribute, but then M is too small for the parallel 4 to really exploit the memory hierarchy of the target device. So it really depends on N and M if that's a good idea. And this is why I used the collapse clause so that the compiler can generate code as good as possible or as good as it knows or as good as it can with its knowledge about the target architecture. Is this a reasonable answer?
Yes, it is. All right. Okay. I think in the interest of time, we have to continue with slides.
Yes. Okay.
Right. But keep sending questions to the chat. I'll do my best to answer them while Christian is talking.
Yeah. And sorry, whenever I want to go back to the Zoom window, I first have to cancel the presentation mode here. I'm not sure what happened since the last update. Something's not working quite as I'm expecting it to work. And this is why I was switching back and forth between the windows here. Okay, unstructured data movement. This slide does not quite look how I wanted it to look. Again, there's a formatting problem. So the title is Map Variables Across Multiple Target Regions. This is the idea here, and Michael will talk in more detail about that later on. But remember what I briefly showed you with a Jacobi code. There were two, let's say, compute-intensive for loops within the while loop. So, and the while loop was running for at least 100 iterations, or sorry, at most 100 iterations in this particular example. And from what you have learned in the previous webinar, that you have a target construct with a map clause for each target offload, the data environment on the device has to be established. That means data has to be copied from the host to the device before the target kernel or the GPU kernel is being started, and then it has to be copied back from the device to the host. And again, remember, it might not be a copy. It depends on your device. This is why OpenMP uses the terminology map. We discussed it last time. And what I did to the Jacobi code is that not only for the two kernels that follow each other, but for the whole while loop, I made sure that this variable, this is array A, is being held on the device, and a new, the other array, is only, or technically it's a matrix, is only allocated on the device. That means there's no instance of this matrix on the host. And this is the basic idea here with separating the data mapping from the target offload or the kernel offload. We can improve the efficiency of our code on the device. And we have different constructs for that. So target data establishes a so-called data region. That means it has an extent that is being derived from the curly braces. And at the beginning of the target data region or the data region, data is being mapped. And at the end, data again is being mapped, possibly with different directions. But now to the topic of this presentation, we also have target enter data and target exit data, although it's hard to read here. And these allow for so-called unstructured data movement. That means at a certain point in the code, you can move data or map data, that's a better term here, from the host to the device or from the device to the host. In addition to that, we have the target update, and that again, without the need for being at the end or the beginning of a kernel offload, we can synchronize data between the host and the device. Michael will talk a little bit more about tuning strategies. I want to now give you the ideas of the concepts. So target data spans a data region, so it has a structured block. And at the beginning, you can do some mapping, and at the end, you can do some mapping, very similar to what we have discussed in the previous, we have discussed the clauses in the previous lecture, I believe. And with target enter data and target exit data, you can specify mapping at a certain unstructured point in your code. For example, if you have a class in C++ that makes use of the GPU, and in the constructor, you want to, for example, establish a certain data structure on the GPU, and in the destructor, you want to destroy or to free this data on the GPU. You can make use of that because then the target data region could not be instantiated within your class. So it means in the constructor, you could call it target enter data, and in the destructor, you could call the target exit data. And with that, you can achieve this data environment on the GPU in a way that, like I just described it. Good. Remember, what happens? This is a default. You have the target data, and you have the target code that might be executed here on a specific device. Be careful with that. Because with that, your code to some extent becomes dependent on a certain architecture of the host on which it's being executed. So the first kernel here executes a parallel for over an array of loop index variable I and does some computation. Then it's doing something else on the host. And then the second kernel performs another code again on the device, again for this I loop. So we have two kernels here, both work with a variable TMP. It's an array. So this one, the first kernel is writing to it, and the second kernel is reading from it and storing a result in res. Now, what is this target data region doing? It allocates TMP on the device. We don't need to copy it because it's being initialized on the device. And it copies the input from the host to the device, or maps the input from the host to the device because this is needed here. it ensures, because the data region starts here and ends over there, that TMP and input are being in place for when the first kernel starts and are still available when the second kernel starts. Yeah? And at the very end, it maps the variable res back from the device to the host, because we might need it on the host. So that's the idea of the data region. I hope you can see this on the right-hand slide here. This is now covered on my view with a Zoom chat window. Sorry for that. Okay. Oops. We can also, and I mentioned it, yeah, synchronize variables that are already mapped with a target update clause. So sometimes we want to exchange data between the host and the device. And with that, I mean both directions, while a set of kernels is already running on the device or in between a set of kernels. So that means we want to have a synchronization of only a part of the data environment. So it's a similar kernel as shown in the previous slide. So here's the first kernel. This is the second kernel. But now we do something on the host. And so we update the input array. And that means after the first kernel on the device has been executed, there has been an update to input. So that means the second kernel has to take that update into account. So you see that the code has been changed here. In the 2 slides ago, input was not red, but now, input is red, but now we have to understand that input has been changed here. 2 slides ago, this was just do something on the host. So the target update is a statement that's encountered and then the data transfer is being initiated, updates the input array. And I think the 2 has to be in the parentheses here. Sorry, this is a typo. So it's a 2:input. So it updates the input, taking the current version of the host and overwriting the version, the very instance of this array on the device. So in addition to the data region with a target update, you can initiate in both directions data synchronization of mapped variables between the host and the device, and it doesn't have to include all variables, but only those that are selected with the corresponding map clauses. No, oops. Okay, let me show you a little bit clearer example. Sorry, Zoom is reacting strange for me today. I have to close this window. I can't see most of my slide. Let's see if it works better. Yeah, I can see my slides. I hope you can also see the slides, Michael. Does it look okay?
Yes, and some shaded boxes gone from the slides as well.
Oh, so, yes, okay. So this was getting larger for me whenever I clicked. I was almost unable to read the code. So, okay, now I'm back. With having said that, data environment and target update, I wanted to show some examples. First, again, a little bit, a slightly different code to explain in more detail the data environment, and then the updates between the host and the device. So this is a vector multiplication, not necessarily a very efficient one, because it partitions the vector. So let me see, P is a result. This is being mapped from the device to the host at the end of the data region. This performs the first computation, and this is then the second compute kernel. And we do some init again in between the 2 codes. So that means for each kernel launch, we have to map V1 and V2 from the host to the device. First for the initial one, and then because we do an init again, we have to again map it from the host to the device. So This is structured mapping, target data. It spans the target region. So that means from here to there, the variable P remains on the remains valid on the device, and at the very end, it's being mapped back from the device to the host. And V1 and V2 are being mapped at each target construct, just as I explained it. Okay, so structured data movement or data management means we have a well-defined lifetime of the data on the device. Now let me explain what we can do with the target enter and exit data construct. So take a look here now at the different init and output functions. So this is saving a little bit of code, referring to the C++ example that I showed earlier. So in the init, we call pragma-onp target enter data, and that performs an allocation of P on the device. And if we take a closer look at the code here, init is being called here. Yeah? And this could be the constructor, that could be your initializer. So with that, we're independent of a C or C++, of a C++ example. Yeah? And remember, here we don't have a structured lifetime. Yeah? So this is like a statement that you would encounter, and it initiates the data transfer. And then init is being completed, but the data resides on the device. Then the kernel is being executed. Again, V1, V2 have to be copied from the host to the device because of the special way this code is being written, or whatever has been assumed behind this example. We execute the kernel, and then we have the init again. So we have to update V1 and V2. We have to map it again, and then there's a output routine which contains a target exit. That means P is being mapped back from the device to the host. So P is allocated on the device in whatever initializer your code is using, and then the result is taken back from the device to the host whenever you clean up the device environment. So with that, I think I covered the idea of unstructured data movement, because here we don't need the static lifetime of a target construct or a target data construct, but instead, independent of that, we can initiate data transfers between the host and the device. And I also covered the target update construct to manage the synchronization of map data between the host and the device. Michael, I would switch over the speaker function, the presenter function to you, or are there any questions that we should cover at the moment?
No questions. I answered all of them in the chat for now.
Thank you very much.
All right, let me talk about some more details on what you just heard. All right, so optimizing data transfers, as you already have heard from Christian, and he was showing in the in the example, the hands-on, optimizing data transfers is really key to performance. And let me show you why this is. Okay, so you've seen this picture earlier in the fourth webinar. We have the host, we have an attached accelerator or many of those, and then there is some communication link in between the host and, in our case, the GPUs. Now, the typical thing that happens is when you look at the different bandwidth that are available. So say you got your host memory, you got something in the order of hundreds of gigabytes per second. Like, for an AMD EPYC system, you're somewhere in the 350 gigabytes per second range. The bandwidth of the accelerator memory is like terabytes per second. So, somewhere north of 1 terabyte per second, depending on which kind of GPU you're looking at. And in between those two rather high bandwidth domains, you got a lower bandwidth, higher latency interconnect, and that's PCI Express Gen 4. So if you think about a 16 byte PCI Express connection, you get like tens of gigabytes per second. I think it's on the order of 28 gigabytes per second, like 90% of the peak gigatransfer rate that PCI Express is specified for. Okay, so with that in mind, what you got to do is you have to be careful about when you do a data transfer. And if you don't absolutely have to do that data transfer, you must avoid it. And on the other hand, which is not written on the slide, but I'm going to say it, you have to transfer bulk data, right? If you are transferring just a few bytes, you're completely latency bound, and PCI Express kind of only achieves tens of gigabytes per second for rather large buffers of multiple of megabytes, like 16 to 20 megabytes. That's kind of the lower limit where you start to see that much higher gigabyte rate. So coming back to avoiding unnecessary data transfers. So what you have to make sure is that you only transfer what is actually needed for the computation and nothing extra. And on the other hand, to make the lifetime of the data on the GPU as long as possible. Like Christian was showing that already, pretty much, uploading the A array once, allocating, and thus avoiding the data transfer, the temporary arrays, and then keeping both on the GPU as long as possible. And then when you finish the computation, you pull the result data back and post processes on the host, if you will. All right, let me now give you some more details about how OpenMP thinks about those data transfers. And there's something that I already mentioned last time, and I'm gonna kind of repeat it and give you more in-depth detail about what is going on. And this concept is called the presence check. So you've seen constructs that didn't have a map clause. And I'm showing you an example here. That's a Saxby code again. And here I'm not doing any map clauses, right? And if you remember in the last webinar, we told you that OpenMP implicitly adds something like a map clause and tries to figure out that X and Y are used on the target device, and it's going to add corresponding map clauses to the target construct. And I had a kind of a yellow sticker to the code that said, actually, it's not a map clause that is added, but it is a presence check. So what OpenMP actually does is it adds these, these are fake clauses, if you will. This is just pseudo syntax so that I get the point across. But pretty much what happens is OpenMP tries to determine if Y has been mapped before. And if it is not present, it's going to initiate a corresponding data transfer according to a similar map clause that has a similar effect as map to from. Right? That was what I was showing last time. Okay, and to do this, OpenMP internally maintains a mapping table that records if you have a array Y on the host that has a certain address in memory, and then it remembers in that mapping table the address of Y and the address that this thing was mapped to in the GPU, right? And in this mapping table, if a host pointer is not present, OpenMP knows that the data hasn't been mapped before, okay? The next thing that happens, this is the translation that I already mentioned. The next thing that happens, if you have a construct that doesn't have a map clause for a particular data item, this presence check kicks in. It looks up the variable in this translation table or in this mapping table. And if that data has been mapped before, so OpenMP already knows about the translation of the host address to the corresponding device address of the associated variable in the GPU, right? Then pretty much nothing happens, right? I mean, there's some things that are done internally, but from a logical perspective, pretty much nothing happens. The data is not transferred again. If OpenMP, however, determines that this presence check fails for a particular data item, then it is as if you had written a map to from so that the data is moved over, the mapping is established, the GPU kernel can run on the map data, and then when the kernel ends, this mapping is undone and the data is coming back from the GPU. Okay, Thomas is asking, a presence check would imply that it's not an implicit update. Is that correct? Yes. So, you know, in the case that you already have mapped data from outside and you repeat the very same map clause in here, right? That nested map clause will not have an effect, right? It will then, the presence check part of the map clause will determine, yep, the data has been mapped before by an outer target data, target ended data, whatever construct. And so that nested map clause of the target construct will not have the effect of a data transfer. Right? That's a bit confusing at times because people think when they write a map to, they always initiate a data transfer. And there are modifiers how you can do this. But the default behavior, unless you ask for, is to just do the presence check. If data is already present, then the map clause will not have an effect. All right. Now, what you can do, how you can compose this, and Christian was already kind of giving you some examples. So, you know, at the call site of Saxby, right? This is now the same code as before. You can now have a target data map to X. So you can now transfer the X array up here, and you can do the map to from in an outer scope. And then when you call Saxby, right here, the presence check will say, yep, Y has been mapped before by that map clause, and the and it's still active because we didn't reach the corresponding end directive. So in here, the presence check will determine for Y that it has been mapped before and will do nothing. And for here, for the X array, the same thing will happen. It will look up X in the present table or in the mapping table, and it will figure out that it had been mapped before. All right, and that's something that you can now exploit in all sorts of combination, right? And we already had this question in the chat. You can, of course, nest those constructs with each other, and you can mix them. So you can mix target ended data, target exit data for one buffer, and you can use target data for another. And we will see an example later today about this. Okay, how is the from part of the to from handled in such a map? I cannot really parse the question. I don't know what the how is that I need to answer, but maybe you can refine that question and I'll come back. It's obviously not just a presence check. Well, technically it is, because when you do a from, OpenMP will have to allocate a temporary array for that thing, right? And the funny thing is, if you have like a map to from here and you would add a map from here, that map from will not have an effect, right? Because the presence check will say, you know, that data item has been mapped before. Even though I didn't want to mention it, but there's an internal reference count. So, you know, when you do the maps, one of the things that happens internally is that the reference count is incremented. And when you do the corresponding map froms, or, you know, the from part of a to from clause, or you do a target exit data, then that reference count is decremented. And when it reaches 0, the data is actually coming back from the GPU. Right, so I hope that this answers at least roughly your question. All right, let me show you a different example in C. Pretty much the same idea here. You know, you can combine these things with allocated temporary array. Then the map2 can upload A and B to the device. It can upload C and then bring it back when we execute the closing curly brace. And so what happens is, you know, we are now changing names here, right? On the previous example, I was using X and Y for the same kind of array, but what happens here is, here we are feeding the zeros kernel with the temp array, and in the zeros kernel, this array is now called A, right? But still, the compiler and the OpenMP runtime system will be able to figure that out, because the presence check is not tied to the name of the variable, but the pointer or the memory address behind that variable, right? So here, we allocate temp, we pass it into zeros. Here, the presence check for A, right, which is coming in and happens to be the pointer TMP, will determine that A is already mapped via that map clause up here, and it will run that kernel in the existing data environment. And when we end the zeros kernel here, there are no data transfers happening between the host and the GPU. The only thing where I kind of lied to you is the N here, which is obviously uploaded to the GPU so that the kernel knows how many elements to process. And then we can go through, and Saxby will do the same. So here we're passing TMP in, which happens to be the Y array. And so, again, the presence check will determine that this array has been mapped before by the corresponding target data construct, and will run the kernel in this pre-existing data environment. And then when we kind of, in quotation marks, execute the closing curly brace down here, right, which ends the target data construct, then the allocation is discarded, the buffers for A and B on the GPU are destroyed, and C is copied back, and then also the C buffer on the GPU is destroyed. All right, there's a question. With OpenMP target, if the variable X is not found, will be also mapped using map2 from X enhanced? Yes. If X is an array and you didn't map it before, let me probably go back. So if you would cross out that thing here, you wouldn't write it. Then here, the presence check would determine that X hasn't been mapped before. And then OpenMP would behave as if you had specified a map to from for X on that target construct. All right. Back to you, Chris.
Yes. And now I'll do my best to not get confused by myself with Zoom here. And while saying that, I almost confused myself. Something is completely different today. Sorry. Yeah, and I really had a hard time working with my slides in the first part. Let's hope it becomes better now. So what did we learn so far? We learned a lot about data management, target data, and target enter, exit data, and target update. And if you have, if you closely looked at most of these examples, you will have seen that they more or less use 2 or even more kernels on the GPU. So what we now would like to cover is how to asynchronously offload to the GPU. And that's important if you have multiple kernels. And that's important if you want to make use of both the host and the GPU or the devices simultaneously. And it's actually important if you transfer large amounts of data between the host and the device, because then you can make the offloading a kernel in itself. So the switch from synchronous now to asynchronous use of devices is really, let's say, the gold standard in accelerator programming. Okay, remember, all those target synchronizations by default are synchronous. So that means the host kind of blocks, or doesn't make any progress while the kernel is being executed on the device, and also while data is being transferred from the host to the device. And of course, also this holds true for the other direction. And this applies to both the target construct without the data construct that we discovered and explored this in this webinar, and all implications of the map clauses. When we introduced tasking, I think that was 2 or 3 webinars ago, we said, I motivated this to some extent because asynchronous computation, like what you can do with tasking, will extend also to the device programming. And at the end of the day, executing a kernel on the device is something like a synchronous task. The control flow of the thread or task executing the target changes to the device and then comes back. And we have tasks on the host by default being asynchronous. And now with a no-wait clause, we can make target tasks, so that means the kernel offloading, also asynchronous. So the idea is that a kernel launch is initiated and then the host can continue, or the data mapping is being initiated and then the host can, again, more or less immediately continue. So this no-wait clause is really special in the context of device program because it enables us to make all device operations asynchronous. And with that, I mean as asynchronous as possible. And with that, I mean as good as your implementation is. So a valid implementation could mostly ignore that. But you will see that because all the underlying low-level device APIs do support asynchronous programming for the device, most OpenMP implementations I have worked with do honor the no-wait clause reasonably well. So remember, that's the default here. We have the target map and then the kernel. And while we execute this on the device, the host is kind of sleeping. So that means the host is waiting while the device is busy. And if you spend, let's say, thousands of dollars for your host CPUs and again, thousands of dollars for your host GPUs, I think it's obvious that your goal should be to make use of both more or less simultaneously or more or less all of the time. Okay, let's take a closer look at as a simple example. So we have, again, this vector multiplication here with a here I removed some complications, so there's only one in it. Let me show the presenter mode here. Oops, sorry. So there's only one in it. I eliminated the second in it. Otherwise, you know most of the code, but here something's different. Now in the first kernel, we execute for only half of the vectors. And in the second kernel, we execute the other half. So that doesn't make any sense from a performance point of view. This is just an example to illustrate the functionality. So what happens? We have the data region. That this is a Fortran code, starts here and ends over there. It does a to from on vector 1, 2, and p. And this is now possible because we eliminated this init again, or the second init, or whatever it was called. And now we have the target no wait in front of the parallel do. That means this kernel is being initiated onto the device or offloaded to the device. And the host more or less immediately can continue, encounters the next target, again with a no wait, and initiates the target offload. And then here it waits at the end of the target data for the completion of the kernels and also then performs the cleanup of the data environment. But here we have now 2 kernels that can be launched independently. Again, this is not a good idea with respect to performance, but it illustrates that we can have 2 kernels that can be executed on a device more or less simultaneously. But it also illustrates that we might have dependencies between the kernels. So if the second kernel would make use of some data that's being used, modified, whatever in the first kernel, then we would need dependencies. And remember, again, our introduction to tasking. We have task dependencies, and now with device tasks, we also have the depend clause in order, or with that being able to express the same kind of dependencies. So that means we can introduce dependencies between the tasks that are being respected by the runtime to make sure that the code is still correct while expressing as much parallelism as possible. Let's take a closer look with some examples, but I would also like to motivate you to think about, let's say, truly heterogeneous computing. Truly heterogeneous is nothing that's well defined, but with that, I mean, you want to exploit the host and the device in the same way. This is not easy, it's tricky. And for some code, it actually might not be worse at all. But for many codes, this is what you should aim for. So for this very simple example of a matrix vector multiplication, the goal would be to execute, let's say, some part of the code on the GPU and some other part of the work, not of the code, of the work on the CPU. Obviously, this is not a programming challenge, but also, let's say, a challenge of performing the right load balancing, because you have to estimate how much is a GPU, for example, faster than the CPU for the particular workload. And some data structures might have to be replicated. That means they might have to be available both on the host and the device. I've seen many applications where it was successful if you know the load. That means the computational cost and in consequence also the speed of the operations both on the GPU and the CPU. But if this is not known, then it becomes really tricky. But remember that you have in most compute nodes 2 pretty powerful CPUs as well, and you should not let them sit idle for too long. They need power, and you have paid, or your compute center has paid a hefty price for these CPUs as well. If you think about this, partitioning the work between the host and the device and executing both, there are a couple of, let's say, tunables in terms of the offloading process that you could try to exploit. So remember that in asynchronous launching or data transfer, the control returns immediately to the host. So the launch is initiated, but it might take a while until data is there, until the kernel has been executed, and obviously until the kernel has been completed. So with asynchronous execution or asynchronous device capabilities, it allows you to really make use of the both devices. That means, and I said it, now let me explain it in more detail. This is a CPU. And from what we have seen so far, whenever the GPU was in use, the CPU was idle. Our goal is that whenever the GPU is in use, the host also does something meaningful. And if you remember back to the Jacobi example, I have a version that makes use of both the CPU and the GPU. And there was this particular statement meant for this situation was a statement meant for denoting how many of the rows were executed on the host. In the code that I've shown so far, it was only 0. But for the Jacobi code, you can explore this load balancing problem on your own. With asynchronous executions, you can also overlap the PCI transfers or whatever link you have between your host and the compute device in both directions. So that means while the GPU is busy computing and while the CPU might also be busy computing, you can initiate the data, or you can perform the data transfer for the next compute task. That's the idea, to keep both the CPU and the GPU and the path between both as busy as possible. So this is the GPU with its memory, the CPU with its memory. And on most systems, you can have at least 2 transfers in both directions simultaneously active before you, and you need that in order to actually exploit the bandwidth of the devices. And I think I mentioned it, you can overlap the data transfer and the computation. Have the GPU compute, let's say, on a part of this matrix vector multiplication while transferring the other part of the matrix simultaneously. And with that, you can solve the problem faster, because after the first amount of data has been transferred, the CPU can start the compute. So you can speed up. But you can also make use of that in order to process problems on a GPU that are larger than the memory that is available on the GPU by partitioning the overall problem into smaller pieces and transferring them chunk by chunk. And if you do it right, you can not only make it, let's say, solvable on the device at all, you can also speed up the computation. If resources are available and if your kernels fit, you can also execute multiple kernels on the GPU. But again, there it really depends on your target device, how many kernels it would make sense to run on this GPU. In particular, they should not become too small in order to minimize the need for synchronization on the device. And I think we covered that in the previous lecture when talking about the degrees of parallelism for a GPU. So I hope the idea became clear. So, okay, final animation, sorry for that. So we could have larger problems and also smaller problems in chunks and so forth being executed in simultaneously, and while also data being transferred between the host and the device, and possibly even computations being done on the host. I said that with a no-wait clause, you can make the GPU operations asynchronous. And with dependencies, you can express dependencies between different tasks on, or let's say, kernels on the GPU. But with that, you can also operate on the host to make sure that kernel offloads and data transfers are also executed in the right order. For example, that the kernel offload only starts after the data transfer has been completed. And because we made all of these things tasks with a depend clause, there's also the task wait with which you can synchronize asynchronous operations. I have examples on the following slides. But this is the idea here. We have a target with a map. We call it a no-wait. And we have a dependency, which is an output dependency of a, let's say, data field named GPU data. So this target executes and goes away. That means it transfers the data that's part of the map clause and executes then the kernel. And immediately after initiating the transfers, the host returns and then execute a task on the host, again with an output CPU data. Here's another task on the host, which depends on the previous task. So this one has to be completed, but it also depends on the task on the device. So here, this task will wait for both previously generated tasks to be completed because they have output dependencies. That means they provide some values, some data in these corresponding data fields, while this task has to wait for the data because it has to consume the results. That's the idea here. If both previous tasks are completed, these dependencies are fulfilled, and then again, we can continue with work on the host. Here's a task wait that will finally wait for all tasks, and in fact, it only waits for this task to complete. So that's the idea of an asynchronous kernel offload with a no-wait clause. So it will immediately, the host will immediately resume and continue, and with that, we can keep the host busy while the GPU is busy with a data transfer because of the map, and the kernel because of the target. And we can wait for this to complete again with the dependency clauses as I just outlined. I hope that makes sense so far. Now, let me take a closer look at two code examples here. Or are there any questions, anything that I should cover at the moment, Mike?
No, I covered everything that was coming in the chat.
Thank you very much. So this is, again, vector multiplication in an asynchronous way. Again, this is not meant for efficiency or anything like that. It's here to illustrate several different aspects. We have a target enter data, which allocates V1 on the device and also V2 on the device. We have a target output, target no wait, sorry, asynchronous with an output dependency on V1 and V2. That means it will probably compute something and provide the results in V1 and V2. It's an asynchronous task, so this on the host can execute immediately. And here the assumption is that other work, which is executed on the host, does not involve V1 and V2. So we can have the GPU busy and the host busy. Here we have again the target, a no wait dependency with V1 and an independency with V1 and V2. So that means this task waits for this task. It contains a parallel 4. So again, this is a task and a kernel that's being executed on the device, but it has an independency. And with that, it waits for the other kernel on the device. So it will be only executed after this one has been completed. And then we have the task wait. So this ensures for all tasks to be completed before we finally clear up the data or clean the data environment. That means the release V1 and V2 are being destroyed. What did I say? I think I explained that. The dependency requirement is also what I explained, and the task wait directive waits at the very ensures that at the very end we wait for all the, let's say, sleeping or whatever incomplete tasks before the data environment is being destroyed. In order to make it clear, now we have a minor complication. Again, we have a target enter data with the allocation of V1 and V2 on the device. Target no wait provides V1 and V2. Okay, no difference here. Now this task on the host depends on V1 and V2. So that means we have to have data back from the device. If we just say task depend on V1 and V2, the task would not start before this previous task has been completed, but it would not automatically, I use this term by intent, transfer the data from the device to the host. So the assumption is that V1 and V2 are being updated or provided or whatever in this function. Now we need it here. We need dependencies in order to wait for this task to complete. But we also need the target update of the from clause in order in order to copy the data from the device to the host. So I understood, from is a correct clause. Sorry, it's not the map clause. I did a wrong explanation in the previous slide deck. So from is a clause. V1 and V2 are the data elements that we want to transfer. And again, we need the depend, because this is asynchronously called. And then the host would immediately execute the update. But the update is only possible, or that only makes sense, after this previous task has been completed, because otherwise we would copy probably incomplete data. Again, this is here to illustrate the functionality, not necessarily to illustrate an effective use of the device. Michael has more details on that in the following slides. Asynchronous kernel launch. Now we have a task on the host that needs the data. So we have to first wait for the asynchronous kernel to finish, but we also have to transfer the data that's needed on the host. And in order for that, we also have to wait for the kernel on the device to complete. How do we continue after completion on the host? Again, we have to update the data on the device. So V1 and V2 are being copied back. So this is being consumed and then updated on the device. We have again a kernel on the device, which depends on this target update. And then finally, we have a task wait to wait for all the kernels before we release the data. So at the end of the day, with explaining all this functionality here, we don't have really heterogeneous computing because either the host or the GPU is busy. But we crafted this example because we wanted to illustrate the use of asynchronous kernels with a no-wait clause, the target update as a way of unstructured data movement, and the dependencies on host and also device tasks in order to illustrate the data flow and the binding correctness on the fulfillment of dependencies. I think that was the end of my example. Any questions at the moment? Many questions in the chat. Michael is busy.
Yes, I was. If you can hand me the beach ball, I can start sharing while
the beach ball is yours.
Thank you. Right. If there are no questions, just keep sending them to the chat window. Christian will take good care of those. Oh, recommendations for debugging such examples with task dependencies. That's a question for you.
Okay, so to be honest, yeah, task and task dependencies are a challenging correctness problem. So there are tools, and to some extent, my group is involved in developing them that can monitor the correctness of also task code with dependencies. So for example, Archer or the thread sanitizer that comes with Klemm. But they only work well if you get rid of this device stuff, because at the end of the day, they verify data accesses and they can only trace data accesses on the host. So for verifying this task dependency pattern, I would recommend to not perform the offload, but just execute these tasks on the host and then use a tool like that. There's also a tool developed at HLRS in Stuttgart, Germany, which visualizes task dependencies. I just don't have the name of the tool available. So it's not necessarily a correctness tool, but it can also help you to understand the dependency pattern of an application. Yeah, so my recommendation is, in order to debug tasks with dependencies, restrict yourself to the host and then use Thread Sanitizer or the Archer toolchain to understand what's going on. Yes, I will look those pointers up. I will add it to the chat. So Michael, please continue.
Yes, all right, thank you. So hybrid programming. In this case, for the next 10 minutes or so, hybrid programming will mean the interaction of OpenMP with a lower level programming model. So something like OpenCL, CUDA, or HIP. So not, hybrid, not in the sense of MPI adding on top of OpenMP. So what we do support in OpenMP is that you can actually call a low-level kernel from OpenMP application code. So what I mean by that is you keep most of your code with OpenMP offload directives, data management directives, and so forth, and you can invoke a low-level kernel that is written, say, in HIP. The other thing that we can support is you can call an OpenMP kernel from low-level application code. So that means if you had written your source code compilation unit in HIP code, then you can actually invoke an OpenMP target kernel from that low-level code as well. And I'm going to focus on calling low-level kernels from OpenMP application code, because that's, in my opinion, the more productive way. Keep most of the stuff that you're writing in OpenMP, and only for a subset of the kernels where you feel that you can get better performance by writing them in the low-level programming model, you're going to switch to that. All right, so here's what I want to do, right? So here's a piece of code, again, evolving around Saxby and some dummy code around it. So basically what we want to do is we have a bunch of computations to compute X and Y, and then we want to do a Saxby on X and Y, and then we use the Y array in another computation. And so let's assume just for a second that this Saxby kernel, if it is written in OpenMP, doesn't give the best performance that you desire. Okay, so let's just assume that for a minute. There's no fundamental technical reason why that could be the case, but just let's, as a working kind of hypothesis, let's assume that. So what I'm doing here is, you've seen these things to a large extent so far. So we are mapping X and Y accordingly, so everything is just fine. And in the Saxby kernel, as I explained, you don't need the additional map clauses, because the compiler and the OpenMP implementation will figure out that the mapping of the data has happened before. All right, so let's now assume that the code that is produced by the OpenMP compiler for that piece of code is not ideal, and we want to re-implement that in a different programming model. Here's the HIP version of this, right? So if you use HIP, this is roughly how it looks like. So this is a traditional HIP kernel where you figure out where you are in the ND range. So in this case, one-dimensional grid, and then you got the statement to compute Saxby for that point in your one-dimensional grid. And then I'm invoking the Saxby kernel using the chevron syntax that you can use in HIP to invoke those kernels. Okay, so this is pretty standard HIP programming. And the question is, how can I call this thing in the code on the previous slide so that this kernel up here will work on the right data and will do the right thing? All right, so the first thing we have to figure out is that these are device pointers. So the way CUDA and HIP work is that you do a CUDA or HIP malloc, which will allocate stuff on the target device. So what you get back from this, from these allocation functions is nothing that you can use on the host. These are the pointers that are only valid on the device, and I'm going to call these device pointers from for the rest of the slides. All right. So for some reason, what we now need is a way that OpenMP already has to translate the host pointer, right? That thing that you used for mapping the data when you wrote the target data construct, right? And you need to tap into that mapping to figure out the device pointer that is associated with that corresponding host pointer, right? And we need to get that, extract that from the table. So what I mean by this is this, all right? So here's the X array with some content and a virtual address in your host memory. Let's call it ABCD, all right? Then when you do the target data map for X, you basically allocate a bunch of memory on the device memory, in the device memory, and let's call that EF12, just a different value, right? And what OpenMP now maintains for you is this mapping table that I already mentioned, where ABCD, the host pointer, is mapped to this device pointer. And OpenMP now uses that information, as I explained earlier, to figure out if data has been mapped before as part of this presence check that we explained, right? And so what we now need is a way to say OpenMP to give out that part of the mapping table so that we can stick it into the HIP kernel and invoke that on the right data buffer. All right. So this is how it works in OpenMP. So there's a clause called use device PTR, and that is exactly the mechanism to do this pointer translation for you. So what happens is if you have some variable X that is pointing to this host memory, when you stick it into the use device pointer clause, what happens inside those curly braces, the original X pointing to that location is gone, and it has been overwritten with the device pointer. All right, so OpenMP kind of shadows the original variable X with another X that now contains the device pointer. All right, and we do that so that you don't have to make extensive code changes to your code, right? If you just cross out the directive, that code will still work because the translation won't happen. But if you have the corresponding target data use device pointer in here with the shadowing, the same code now works on a GPU because that pointer translation has been substituted into the X variable. All right, so putting it together, right? And I'm illustrating, the pointers on this slide. So you allocate X using a regular malloc or stack allocated memory, whatever, and it points to this ABCD address, right? Then we go into the target data map to actually move X over to the target device and establish the data environment on the target device. And now when you are inside these outer curly braces, the mapping table now maintains for X that is coming from this host address, that it has this device address, and the original pointer, right? The X is still the valid host address. So you can just touch it on the host like Christian was showing before. Now to call the HIP kernel, you wrap the HIP invocation or the invocation of the HIP function with the use device PDR. And for X, I'm now showing what happens. The mapping table still says X is mapping from that host pointer to that device pointer. But now the X that you're passing to the function invocation has been translated to the device pointer. And so now it is as if you had called CUDA or HIP malloc and a HIP or CUDA memcopy for that X variable, and you're passing that pointer as you would do in a regular CUDA or HIP program. Does it make sense? I hope so. Christian, we're going to defer for the sake of timing the advanced task synchronization stuff to the next webinar. And make that kind of a catch-all webinar with select topics of OpenMP programming. All right, so let me quickly walk you through the case study that I did for Intel GPUs, NVIDIA GPUs, and AMD GPUs. And this is the NWChem package. This is a renowned quantum chemistry package that is running on large-scale systems. I think the largest run they did is like 1 million cores. And I was touching the TCE implementation. So TCE is the short for tensor contraction engine of the coupled cluster chemical method, quantum chemistry method, with single, double, and perturbative triple replacements. If you don't have a clue what that means, I don't have that either. I was receiving like a 3-hour lecture from the NWChem developers about this. And the only thing they left behind is that I know what CCSD stands for and a large quotation marks in the back of my brain. All right. I said all this. If you're really interested, here's the link. You can go and download the package. Also from GitHub, if you search for NWChem on GitHub. All right, so offload candidates. We talked about this. Pretty much what you need to make sure is that you have something that is compute intensive, highly parallel, and where ideally the compute is scaling stronger than the data transfer. So you want compute to be in a higher complexity class than your data size of data transfer. We already mentioned that, I believe, in the last webinar. So here's one of those 27 kernels that make up this chemical method, right? So all of those kernels have pretty much the same structure. They're massively parallel. They have a lot of computational meat, if you will. There are 7 perfectly nested do loops. Here I'm just showing a kernel that has 6 because the inner one has been fused into a product loop already. And the trip count of these loops is on the order of somewhere in between 20 and 30. So if you have 7 nested loops, that's like 30 to the power of 7. So that's a whole lot of iterations that is running on, in this case, then a GPU. All right, now let's do the naive data allocation, right? We just accept the fact that there's a presence check and that OpenMP will automatically add the corresponding map to from clauses for all the data that we're touching. And so what you'll figure out is if we assume a tile size of 24, we will end up with like 1.5 gigabytes for this array, for the triple SX array, and then 2.5 megabytes for the T2 and V2 arrays, right? So what will happen is, if you just blindly accept that we offload 1.5 gigabytes from the host to the device memory, we run for a tenth of a second, and then we download 1.5 gigabytes of data from the device to the host and store it there. All right. Now let's look at the outer level of how those kernels are actually driven. And here's the structure, right? So what you see when you look at the code, and I just shorten it a tiny bit so that you don't have to see all 50,000 lines of code. You know, there's some communication happening, right? So we receive T2 and V2 from another MPI process. Then there is a loop calling into those kernels. So, you know, 1 to 9, that's the first block of 9 kernels. They have an if condition, so they're not invoked all the time, but you know, you have this sequence of if I need to invoke that kernel, then do so, and that repeats like 9 times. And then there's another do loop that pretty much does the same thing. So if a particular kernel has to invoke, it will select one out of, or many out of those 1 through 9 kernels. And in a different compilation unit, there's another structure that is very similar to that for the remaining 9 kernels, so that you end up with 27 kernels of the same structure. Okay, and then in the end, you know, there's a sum energy. So pretty much the whole 1.5 gigabytes array, that's just an accumulator, right? So you don't really need it on the host. You just need to compile or aggregate all the results that are computed by the tensor contraction engine. And in the end, you just sum it up, and it basically gives you like 2 numbers that you're looking at. So there's no point in actually transferring those 1.5 gigabytes at all. So with that in mind, what we can do is we can use a target ended data that allocates the 1.5 gigabyte buffer or accumulator array on the target device. So no data transfer needed. We just allocate this massive amount of memory. Then we call a kernel 0SSX, like I was showing with, you know, the Saxby examples where we had to zero out one of those temporary arrays. So we're going to call that, that's a GPU kernel that just sets everything to 0. And now we had this question earlier today, if we can map, nest those data mappings. And yes, we can do this. So, you know, here I'm establishing a data environment for SSX that pretty much ranges down here when I release it, right? And anytime I got a new updated T2 sub or V2 sub, I'm going to map that, in this case, 5 megabytes if it's a tile set of 24, and kind of inject those into the existing data environment that already contains SSX. The other thing I could do, I could pretty much move that out here and do an alloc on T2 and just do a target update once I have an updated value for one of those arrays, and inject that into an existing buffer object. Right? Okay, so that one I covered. And then, you know, inside that kernel, again, referring to this presence check, OpenMP will figure out that both or all 3 arrays, SSX, T2 sub, and V2 sub have been mapped before, and it will not do an additional data transfer, so that it, you know, we can save those extensive data transfers in the end and just pay for the compute time that we have to pay for. All right, and finally, you know, the sum energy kernel then is just reducing the 1.5 gigabyte array to like 16 bytes, the 2 double precision floats that are then treated as the energy level that the whole algorithm computes. All right, are there any questions? Yeah, there's one. In the previous example, what happens if you don't specify use device pointer? Will the code crash? Let me go back. And
yes, thank you, Michael.
There it is, right? So if I wouldn't be using that, right? Oh, there's, by the way, a target data. There's a typo in the slides. We'll upload an updated PDF when we hang up. So target data, if you don't use the device pointer, right, what you'll feed in is this pointer, right? And the HIP kernel will pretty much crash with the equivalent of a segmentation fault, because the GPU will report back to the driver, sorry, I don't know what ABCD is. I don't have a corresponding address in my memory. And the kernel will terminate with an error message. All right, so you have to, get out the real device pointer that you would also get from the corresponding HIP allocation functions or HIP memory move functions, because otherwise the GPU will not know what to do with that pointer. All right, that's all I had to say for today. And back to you, Chris.
Yes, 1 second. Still 1 more second. PowerPoint still loading. So there's nothing special to show. I think we are almost at the end of the time, yeah. But with what you have learned so far, I think there are a few things that you can still apply to the Jacobi code. So and I think I made a remark on that already. You could run it in parallel or simultaneously on the host and the device. And there are other tunables that you could deploy. So the challenge would be to run the code as fast as you can. And having posted task to other audience at workshops or lectures, some people came up with very clever and interesting ideas to speed up the code. So if you're interested, we could discuss it next time. That's all I have to show and tell at the moment. And a little bit later, we can upload solutions to the code, illustrating, for example, the simultaneous use of the host and the device. Any questions at the moment? I have a question in the chat, sorry. A question about loop collapse. I think the loops have to be perfectly nested without any code in between. I think the compiler will complain, and that means you would have to move the initialization to, for example, the inner loop. Yeah? And that should be possible if the loop indexes do not depend on each other. Thinking about it. Okay. Then I think that's it for today. Thank you very much.
Thank you very much, Christian and Michael, and thank you everyone for attending and all the question and discussion. So for the reminder, the next webinar on OpenMP is on Thursday, 24 June. And then we have another one scheduled in September that will be more open question session. Okay, thank you everyone for attending. And